This is the last try at this because apparently when I type it's very loud, so it's not good. So alright, let's try and explain this as fast as possible. So here you have your plasmid that you can see. It's called GA1 Gibson, so it's an old Gibson reaction that I made where I added this gene 10. What I do not want to have is having the gene 10, and I want to replace it with the gene 2 from GA1 phage. And this is our phage. It's 21 base pair long. 21,000 base pair long. Alright, so we've got this thing, and what we want to go under is we want to create a new assembly and select Gibson. So here we are now selecting Gibson, and we click on Start, and we're going to want to see the sequence map. Now this is a typical plasmid that you have for protein purification, and one thing to note, especially for the people who are starting out here, is that especially if you use it for protein purification, it's not going to start on an ATG. The ATG site, so the start sign, is located right up there. So be careful when you select the gene that you want to clone not to include this ATG site. So this will be GA1, this plasmid called GA1 Gibson. Sorry if it's a bit confusing. It's called GA1 Gibson. We're going to want to select everything but the gene. So everything but gene 10. So now I've selected gene 10, and the easiest way to select everything but that is to actually invert the selection. So now I've selected everything but gene 10, and it will help us replace gene 10 with gene 2 from that phage. And so the reason why we do it via Benchling is that Benchling is going to calculate the correct primers via the primer 3 algorithm, and will determine the actual correct melting temperature and the correct length for those primers with the optimized settings that you give it. So now that I've selected everything but that, and I'm going to click on backbone and click on set fragment. So this is my, here it's showing how it's going to be linearized, and this part right there is going to be what I want to insert. So you'll see that one of the ends is ending in TGATC, and that is one of the ends. Well, actually, no, sorry. I take that back. This is everything that you have inside this backbone, and this is where it will join up on the ends. So you see TGAT, bam, this is where the insert is going to go. So this is what you have. Now you click on the insert, and the insert that you're going to want to have in this particular case is gene 2. So because we're with phage, we want to double check that it's an actual protein. You never know how these things have been annotated. And so the first thing that you want to do is create translation. Obviously, why I've chosen this example is because here the protein is actually annotated the other way around. So you want to go create a translation and create a translation in reverse because the gene is going the other way around. Okay? So this is our protein. It has a stop codon, TGA, and it has a start codon, ATG, methionine. So we're going to click fragment. Now, what is it actually telling us? Right now it's telling us that at this end, TCCG, you're going to have your stop codon. That's not what you want. What you actually want is for it to start. Ooh, actually, even if we did that, even if we reversed it, we're going to notice, oh, we're starting with the methionine. But we already took care of that methionine, so we don't want that. So, it's great that I'm doing it with you, so I know What not to include, I'm going to take out that methionine, make sure that it's in line, click on change, and click set fragment. Again, make sure that you're not starting with your stop codon. Oops, set fragment, and reverse it again. So now we're starting with GCT, GCT here, and it's joined up with GGC. Bam. So now we're happy. What we can also do is we could add a spacer. So if we want to add a spacer, for example, we're not happy with the TEV site and we want to add something else, we can write a few bases for, I don't know, anything. Make it a longer tag. And that would be your longer tag. Obviously, write it in multiples of 3. Bam. And now you have a 9 base pair kind of spacer that you have, which will be actually taken into account in the primers that are joining this fragment with this one. So there will be 9 base pair longer in between. But we don't want that, so we're going to remove it. So now we still have this. We call it Hugo's Awesome Assembly. I'm trying not to type very loud. So because I'm using the microphone from my computer, and we want to click assemble, but before we click assemble, we're going to check on the enzyme parameter setting. So we have the minimum melting temperature for the primer's binding bases, and that is the minimum priming so this is the melting temperature which will be used for when it's amplifying, for example, when it's doing the IPCR and amplifying the vector, is going to calculate the base pairs from which it actually binds, and then you'll have this long tail. So this is calculating the minimum melting temperature of what binds here, and that's your for the binding bases. And for the whole binding, you click, and you should keep it around 50 degrees because you don't need much higher, to be honest. And the minimum TM, so melting temperature for the whole primer, you obviously want it the same or equal. I wouldn't go much higher, and I would keep it at that, and that's just calculating the whole primer. So this plus the homology and the 20 base pair homology. Here you can change how long you want it. So 20 base pair. If you do have 20 base pair homology, and you can set the maximum, because obviously these are parameters for primer 3 to calculate. So if you keep it to around 20 base pair, that will give you a 15-minute reaction. If you want to go longer, if you want to put 80 base pair, for example, you have to account for that in your reaction time and your incubation time at 50 degrees. And you probably want to spend an hour because that's the time that the T5 exonuclease will take to chew back. And lastly, you want to pay attention that this is kept to at most 5 degrees, because when you do a PCR, you don't want your 2 primers. So this is calculating the 2 primers, for example, the 2 primers for gene 2. It's calculating that the difference between the melting temperatures isn't higher than 5, and it's not, because that's the maximum. And we click on assemble. Now we want these to be going into our folder that we've created for this, and we now create all the primers for that assembly, and we can see the TM difference and whatnot, and the TM difference is under 5, so that's quite good for our purposes. We don't want it over 5. We can see that there's a little bit of self-dimerization, but you don't want it to go higher than -10. And frankly, right now, that's okay. And here we see the parts of the primer. So the primers are, this one is 40 base pairs, so you take 20 plus 20, that's 40 base pairs. Binding will be 20, so 20 base pair will be binding. It's not going to be any mispriming, and this is under 10. So you don't, because if it's around -10 or less than that, -20, blah blah, that means that it will actually form secondary structures and whatnot, and you really don't want that later down in your assembly. So now it's time to do our PCRs from our templates for the Phage, NGA, and the Gibson. And the way we do that is we go to Hugo's awesome assembly. We click on finalize because we're happy with the parameters. Great. Now we check out the sequence map. So this is one of the primers, and this is the other primers that are going to amplify the backbone, and this is the other one that's going to amplify gene 2 to the other end. Right. So if we double click on it, we can see the full length of it. This is the part that binds, and this is the part that doesn't bind, that does homology, sorry. So we should have AGT at the lower end of it. Let's check if we have AGT correct. So it was going to have homology there. Okay, now what we want to do really is for our purposes, because Q5, so we use Q5 as a polymerase compared to TAT, and Q5 you get compared to TAT, there is no algorithm for it. All of the data has been empirically acquired, and so you need to use a calculator for this. Hence why I tend to copy only the region that actually binds to the template. So this, I don't click on here because here will select everything. I select just the part that binds, copy this, and put it as primer 1. Then I go down and I copy this. So we should have a reaction when we're doing our PCR. Okay, they're both very at the same, more or less, melting temperature. We should have a PCR that should give us a product that will be about 2,800 base pair long. So you can count, so it's about 30 seconds per kb on Q5. So we should give it 1.5 minutes for the elongation time at 72, and the annealing temperature for a reaction for amplifying that backbone. The annealing temperature is going to be 65, and you can give that 30 seconds, and keep obviously the beginning by 98 degrees plus 10 seconds. The melt, whatever it's called, I forgot now. Anyways, that's more or less the cycle, and it should give you this. It should give you 2,807 base pair. Now, let's say you've carried out you've carried out your reaction and you've done your gel purification. So your IPCR is 2,807 base pair long, and your insert, you've gel purified it too, and it's 1,734 base pair long insert. So if you're doing a 2-part or 3-part assembly, I don't think you guys will be doing much more than that, or 3-part assembly, you'll need the vector to be needs to be around 0.03 picomole to 0.2 picomole, more or less, and that's the amount of moles of that vector that you need. And you're going to need either 50 to 100 ng. Okay, I'm trying to type not as hard as possible, because then it'll make a lot of noise. So you're gonna need to see sometimes 50 nanograms of that vector. So let's say you did your gel purification and you get 30 microliters of IPCR product, at around 35 nanograms per microliter. And then the other one, you get 30 microliters. So I always dilute in 30 microliters of insert at around 40 nanograms per microliter. And these are just generic stats that you can get, right? You might get different data. So now 0.03 picomole to 0.2 picomole. Sometimes when you have 50 nanograms of a certain vector, this is where you check the base pairs that you have, it might not equal to 0.03 picomole. So let's check this out. We go to mass moles and we copy this because the vector is what we need. Check out the length. This is in base pair. Make sure that it's base pair and not kb. Make sure this is in nanograms. And the mass that we want, let's say 50. Oh, it's a little less than 0.03 picomoles. So let's give it more or less, let's give it 100 picomoles. Well, actually, let's say we have 105 nanograms because that will give us, that should give us 3 microliters of plasmid, of IPCR product. And that will give us 105. So we're going a little bit over here to what we should have. But anyways, this means that we're using this much. Now what you want to do is go back to ligation. And we say we have 105 nanograms of vector. Switch to base pair and switch to base pair. And to, oh, there you go. And every time you do 2 or 3 inserts in terms of ligation, you want a 2-to-1 ratio of insert to plasmid. And our insert is 1,734 base pair. That means that we will need 129 ng of nanograms of insert. Okay, so now we do, 129 divided by 45, 2.8 equal 2.8 microliter. So we add this all together and we get, we'll use 3 microliters of our IPCR to 2.8 microliters, and that will be in a 2-to-1 molar ratio. So you've seen what we did. We used DS, yeah. Anyways, you've seen what we did. And now you add this all together and you get 5.8 microliters of DNA. You want to make that to 10 microliters, total of 10 microliters. So you're going to add 4.2 deionized H2O, and I will give you 10 microliter DNA plus water, and then you add this to, and then to that you add plus 10 microliter of gibson. And because you've got 20 base pair homology, leave it for 15 minutes at 50 degrees and transform 2 to 3 microliters of reaction. And you should get about 1,000 transformants or so using commercial cells. So say it should be 500 more or less with the cells that we make. 200 to 300 transformants if the reaction is easy. And that's it really. That's more or less that. Thank you.